Look around you right now. Seriously, just take a quick look. Chances are, within arm's reach, there's a small, totally unassuming metal cylinder or pouch. And that little thing is holding enough latent chemical energy to burn a hole straight through your floorboards. We casually slip these literal metal bombs into our pockets, we press them against our faces, and we even sleep with them under our pillows every single day. I'm talking, of course, about lithium batteries. So today, in this explainer, we're going to perform an autopsy on a disaster. We're going to look at exactly what happens when the very devices powering our entire modern world cross that absolute point of no return. All right, let's dive right in.
You know, it's actually kind of crazy when you think about the sheer level of technological trust we have every day. If you crack open one of those boring metal cylinders, you don't just find a solid block of metal. No, you find a tightly wound core. And the only thing, I mean literally the only thing preventing a catastrophic, fiery failure is a microscopic, super thin layer of plastic. It's wild. As long as this flimsy little barrier holds up, your phone charges normally. But if it fails, yeah, things escalate very, very quickly. Because of that super fragile internal structure, lithium batteries come with some pretty strict warnings. You've definitely seen them printed in that tiny text on the packaging, right? Never let them get wet, never expose them to fire or heat, never puncture or disassemble them, and definitely, absolutely never short-circuit them. But let's be entirely honest with ourselves for a second. Do we even know what those safety warnings are really for? To find out, we're going to aggressively cross off every single one of these golden rules. We're going to scientifically violate them, one by one, to see the exact failure modes they trigger. To really grasp the destruction here, we first need to understand the architecture. Think of the inside of that battery as a tightly rolled sandwich. On one side of our microscopic plastic barrier, you have a positively charged electrode made of lithium and aluminum. And on the other side, a negatively charged electrode made of graphite and copper. These two are absolutely desperate to react, packed in as tightly as physically possible, separated only by that incredibly thin plastic sleeve. So, let's move to our first test and see what happens when we introduce our first forbidden element, water. Okay, so there's a pretty widespread myth that the second a lithium battery touches water, it violently explodes. But what actually happens? Well, if you drop it in pure tap water, actually, scratch that, you get absolutely nothing, not even a tiny spark. Pure water is actually a pretty terrible conductor. But watch what happens when you just add a pinch of simple kitchen salt. Bam! The water instantly becomes highly conductive, and this creates an external path for the current to flow right around the battery. It doesn't blow up, instead it suffers this slow, invisible electrical rot, just leaking its energy right through the water from one side to the other until internal failure finally sets in. All right, moving on to failure mode 2, trial by fire. So water is a slow killer. But what if we escalate to a rule everyone intuitively gets? Never expose a lithium battery to fire. Well, here's the incredibly rapid sequence of failure as external heat is applied and the temp spikes. First, the pressure inside that metal cylinder builds up fast. The battery actually has a built-in safety mechanism, a pressure relief vent that pops to try and save itself. But with continuous external heat pumping in, that safety valve is quickly overwhelmed. And that's when the real nightmare begins. The internal chemistry fundamentally breaks down, and crucially, it begins to release heat and oxygen at the exact same time. This leads us to a really terrifying realization about thermal runaway. Once that internal chemistry breaks down and starts supplying its own oxygen and its own heat, the runaway is completely self-sustaining. You can take the gas burner away. You can literally kick the battery across the room. It doesn't matter. It will continue to violently eject burning material for several seconds. Lithium batteries don't explode because of the fire. The fire just triggers a reaction where the battery literally becomes the fire itself. Okay, let's get a bit more kinetic. No external heat this time, just straight up physical trauma. What happens when you take a hardened steel drill and pierce straight through the outer shell at a perfect right angle? The moment that drill breaks through, there's zero delay, no pressure buildup, just a high-pitched humming sound, sparks, and intense fire. Why? Because the drill physically forces that tightly rolled sandwich, the positive and negative electrodes, to instantly touch. This creates a deeply localized hotspot inside the core where cooling is just completely impossible. The energy release is so extreme it actually liquefies the drill bit. And keep in mind that drill's made of high-speed steel. That's a material specifically engineered to survive extreme friction and heat. Yet it just effortlessly melts away inside the battery core. Unbelievable. And this brings us to the so what for everyday damage. A punctured battery gives you an instant, violent explosion.
But a crushed or severely dropped battery, that is essentially a ticking time bomb. Inside that damaged casing, those positive and negative electrodes might be resting microscopically close to each other. They're literally just one slight vibration, one extra bump in your backpack away from making contact and triggering that exact same violent explosion we just saw with the drill.
Which brings us to failure mode 4, the silent short circuit.
We've looked at water, we've looked at fire and physical trauma, but what if we strip all of that away and test a pure electrical failure? If we hook a fully charged cell directly up to thick, low-resistance copper wires, the second that switch is closed, a massive, instantaneous current surge just rips through the battery. We're talking about peak numbers as high as 300 amps surging in a fraction of a second. And because of those insane currents running through that small cylinder, the internal temperature climbs with terrifying speed, shooting straight up to 63 degrees Celsius in almost no time flat. You're sitting there expecting the safety vent to pop, you're bracing for the fire. But then it inexplicably stabilizes. No venting, no explosion, nothing. So why did it survive? Well, because it's a single, isolated lithium-ion cell. The peak amperage might start at 300, but it rapidly decreases in just tenths of a second because its overall energy density is limited. And more importantly, it's sitting all by itself. The heat it builds up can easily escape right through its metal casing into the ambient air, which in this specific test environment was sitting at a cool 7 degrees. A single cell simply doesn't have the energy density to push itself past the point of no return when the heat actually has somewhere to go.
But, and this is a massive but, almost none of the devices we rely on use just one single isolated cell. Contrast our solitary survivor with the reality of a modern battery pack. In an e-bike, a power tool, a laptop, these cells are packed claustrophobically tight together. When that exact same short circuit happens inside a pack, the heat doesn't gently escape into the cool air. It escapes directly into the battery right next to it. And that, my friends, is what leads to the cascading nightmare. The heat has absolutely nowhere to go. Once a single cell gets pushed into thermal runaway, it acts as the ignition spark for every single battery packed around it. That's why short circuits are so unbelievably dangerous. It's not about one battery instantly exploding, it's about the pack architecture allowing failures to cascade unstoppably, domino-style from one cell to the very next. So let's pull all of this together and synthesize this entire autopsy. We ignored every major safety warning, saltwater created an external leak, fire broke down the chemistry, a drill physically forced the electrodes together, copper wires caused a 300 amp surge. 4 totally different mistakes, right? But a terrifyingly clear pattern emerges. They all ultimately triggered the exact same structural collapse, an internal short circuit. Lithium batteries aren't dangerous because they're unpredictable. They are dangerous because once that tightly rolled sandwich is compromised, the reaction violently feeds itself.
It's a sobering thought, isn't it? That incredibly thin plastic layer is doing a ton of heavy lifting for our modern convenience. So the next time you drop your phone hard on the pavement or leave your drill battery baking out in the hot sun, remember what's actually happening down at a microscopic level. It literally just takes one breach for the battery to become the fire itself. So I'll leave you with this final thought. How many tightly packed, cascading nightmares are sitting quietly in your living room right now? Thanks for joining me on this explainer, and seriously, stay safe out there.